Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we look at the derivative of an exponential. So we're going to use this special number here, e, which is about 2.71828. You've probably come across it before. So what I did was draw up a table here where I chose different values of h, and then I substitute each of these values of h into this formula here, e, which is that number there, to the power of h minus 1 over h. So as you can see, as we're going down, h is getting closer and closer to 0. Now, what happens when h gets closer and closer to 0, this expression you can see is getting closer and closer to 1. We write that mathematically like this. So this is what we've discovered from the table. It turns out if I would use any number other than e, which is 2.71828, if I were to do like 2 to the power of h minus 1 over h, I wouldn't get 1. But it's very significant that this limit here is equal to 1. We're going to use that when we differentiate the exponential. All right, so let's now look at trying to differentiate the function fx equals e to the power of x. Again, e is this number here. So to differentiate it, we're going to use first principles, this formula here. So if this is f of x, for f of x plus h, all we do is we take our function and everywhere you see an x, replace it with x plus h. So I'm now going to substitute these two things into this formula here. So we have derivative is equal to limit as h approaches 0. This is f of x plus h minus f of x over h. So we're going to use a bit of algebra to make this easier to work with. So remember, when we're using first principles each time, it's annoying, but we still have to write the limit. So e to the x plus h is the same as e to the x times e to the power of h, because remember, if you multiply bases, you add the indices. So the reason that we write it like this is so we can factorize what's on the top. So I've just taken this expression at the top and taken out a common factor of e to the power of x. All of these lines are exactly the same. So the reason I did this is, you probably know, it's kind of like I'm cheating a bit. I've got this thing here, e to the power of h minus 1 over h. As you take the limit as h approaches 0, this thing here is equal to 1. That's what we found in the table. You see, this thing here, e to the power of x, it doesn't depend on h. So I can actually take it out the front. And as I said, this thing here is just equal to 1. That's what I figured out in the table. So I'm going to rub that out and just replace it with 1. So it's just e to the x times 1, but of course I don't need to write the times 1, do I? It's just e to the x. So this is really interesting. We started off with e to the x, but when we differentiated, we got e to the x. It turns out the derivative of e to the power of x is itself. So what that means is the rate of change of the function at a given point is just the value of the function at that given point. And the reason that this worked, that the derivative of this function is equal to itself, is because of this fact here. So this only works for e. That's why e is such a special number, 2.71828. It's an irrational number that goes on forever. It's the only function where if you differentiate it, you get the function itself. And that has just been proved using first principles. All right, thank you so much for tuning into this video. This has been the luckiest math teacher in the world. Have a great day.